under AICTE CSVTU MOU. I would like to welcome respected Dr. A.S Raghuvanshi sir. Dr. Raghuvanshi sir has received his BTech degree in Electronic and Communication Engineering from the Northeastern Regional Institute of Science and Technology, Northeastern Hill University, India in 1993. He taught in College of Science and Technology, Phuntsholing, Bhutan from 1993 to 2007, the only government engineering college of Bhutan. He obtained his PhD degree from the Department of Electronics and Communication Engineering at Motilal Nehru National Institute of Technology, NIT Allahabad, India in 2012. In past, he has taught from 2010 till 2013 at IIIT Allahabad. Till date, he has more than 50 SCI and Scopus Index research publication in different journals and conferences. He is currently working as the head of Department for Electronic and Communication Engineering at NIT Raipur. His research interests are in area of data communication and networking with application of artificial intelligence and machine learning for data aggregation and intrusion detection in wireless sensor network and Internet of Things. Sir, we are very pleased and honored to have you with us, sir. And I request you to please continue the session. It would be definitely very, very beneficial for all of us. Should we start, sir?
Thank you, sir. Are you able to hear me?
Yes, sir. Yes, sir.
And actually, have you given me the rights to present?
Okay. Okay, sir.
Yes, sir. You can present, sir.
Okay. My presentation is visible?
Yes, sir. Yes, sir. It is visible to all of us.
Okay, then thank you very much. I'll start my session. Okay, good morning, everyone. Actually, it's right now, yes, good morning. So the topic that I'm going to touch upon is machine learning based anomaly detection for IoT, Internet of Things. So these are the table of content, or the way I'm going to deliver this particular presentation. So we start with the first thing we start with is introduction of IoT, that is Internet of Things. We'll see what exactly is Internet of Things. Then this is IoT. We start with this one. So the Internet of Things that we will talk about, we'll see this term. Then we'll come to the data gathering part by Internet of Things, which is done by WSN or wireless sensor network. Then we'll look at the challenges and issues in wireless sensor network. Then we talk about AI, machine learning, and deep learning. Then we'll go to the machine learning in IoT. Basically, where in IoT we can use machine learning. Then we'll see the application of machine learning in IoT, and then we'll talk about anomalies and one particular application of machine learning that is developed by me only, and that was basically an intrusion detection by anomalies in IoT, and then we'll see the publications that I have. So this is how we are going to go. So we start with the first topic, that is introduction to Internet of Things. So first of all, the technology IoT brings people in connection with the internet, which opens a large area of implementation for business and applications. Then the technology of IoT opens large field of wireless sensor network get utilized for trade and sense data over large scale network. In general, IoT systems they can be divided into two parts. One is data delivering part, and other is manipulation of data. So first is how the data delivery part, and then how the data is manipulated. So we first try to answer the question: what exactly is Internet of Things? So internet. So these are the way. Then I'll give you a actual definition of IoT. So Internet of Things that comprises things that means anything that has a unique identity and get connected to internet, it becomes a part of Internet of Things. So this is very generalized way of saying IoT. The focus on IoT is the configuration, control, and networking of internet devices, and these devices we call them as things, and that are traditionally not associated with internet. So actually, the where the IoT is important, where things basically are non-human. So humans, I have always been part of internet, and these things work for human. But sometimes when these things can connect themselves to internet, use the power of internet without actual intervention of human, that is pure IoT. So the things that we can have is it can be as simple as a pump, an energy meter, a washing machine, a car, or anything which is connected with the internet, and it has a power to send data and receive data from internet. So this is very generalized way of talking about Internet of Things. So actually, IoT we can say is a new revolution in capabilities of endpoints that are connected to internet. So this is we can say a new era, a new revolution, which can bring a number of things to internet, and that is IoT. So this is the formal definition of IoT. So first definition is which is given by IEEE. A network of items, each embedded with sensors, which are connected to internet. So this is IEEE definition. So basically, it is a network of items or network of things, each embedded with sensors. So these things they have their own sensors, which are connected to the internet by some manner. So this is the formal definition of IoT by IEEE. Then ITU, International Telecom Union, also gave a definition that is a global infrastructure of information society, enabling advanced services by interconnecting things based on existing and evolving and interoperable information and communication technology. So this is more broader information definition which is given by ITU, and this is basically interconnected things, and it not only uses the today's technologies and today's protocols or today's already existing technologies, but it is also evolving. That means that new and new protocols are coming up, new implementation are used, and latest communication technologies are utilized. So this is more broader definition of IoT. Then IETF, that is your Internet Task Force, they have given this definition, that is IoT will connect objects, that is things around us, to provide seamless communication and conceptual service provided by interaction and cooperation of objects will be in the manner to make services better and accessible anytime, anywhere. So this is the formal definition of IoT. That means these are the things which are connected to the internet, but the important terms which are here is anytime, anywhere. That means the information which is available on these connected objects will be available all the time and irrespective of place where you are. So anytime, anywhere, when this information will be available to you, that is actually IoT. So things connected to internet and information that they are producing or they are using is available for everybody globally. So anyone at any time, anywhere in the world can look at those information without problem. So that is ITF, IETF definition. So if you look at the evolution of IoT, so IoT evolution is right now the time. This is time scale. So before internet, we had pre-internet era. So pre-internet era, the communication was basically human to human and fixed and mobile telephony. That is your SMS. So these were the initial pre-internet time. The SMS what we are talking about are pages. That is, there were some pages which can send text document, text information from one place to another. So that was simple mail, your simple messages, and that was being used by pages. So this was pre-internet. So pages were there. You had telephones. You have mobile phones. You have mobile telephony. But most of the time, mobile telephony that we had was where basically it was voice and SMS only. Then came internet, which was in around 80s, and WW developed. That's called WW. That was your WWW era when the smart networks came, and you have then the information we can send onto the network, and internet came. So that was internet of content. So you have contents available, and people go and this is from 90s till 2000 plus. So that was a time when contents were available and it was new. So email became important. Your informations were available on the net. You just search the information, get the information, and we use it for entertainment. That means you can download movies, you can see the things, and so many other things. So those were there with the internet, but it was very slow. It was not as fast as we have right now. So that was your internet of content. That is when WWW came, or World Wide Web it came. Then this World Wide Web, your WW is called Web 2. That was the Internet of Services. When the same internet that was being developed, we started using for certain small services, like email was there, e-productivity was there, then e-commerce, where you can order a book through internet and get the book which you are still having, which is part of your e-commerce, but not in a very large scale. Then after that came the Internet of People, when the social media developed. So you had number of social your platforms that came, like Skype, Facebook, YouTube, and there were many were there, Orkut, which developed, and people were able to use this as a social media. So that was Internet of People. Then after 2010, and we can say right after 2015 and around, we developed machine-to-machine protocols where things can get connected to internet without intervention of human. So that machine-to-machine protocols gave birth to Internet of Things. So today we are in the Internet of Things, and with Internet of Things, we have smart devices, smart objects, smart data, and everything where this smart world comes uses IoT. Like smart cities, you have smart homes, all smartphones. So all these are basically when internet we are using to send information, analyze information, get the intelligence out of information. That is your IoT. So this was basically how the IoT evolved with time. Then what is the scope of IoT? So the scope of IoT is not limited to just connecting things and devices, appliances, or the machines to the internet, but it allows these connected things to communicate and exchange data. And during this process of communication and exchanging data, it can analyze and process the raw data so that we can extract the information. So the information can be extracted from the raw data, and which can be used to take informed and wise decision ultimately. So it collects data at the ground, it analyzes and processes the raw data, extract information, and provide this information to at the highest level, so that the people at the highest level can take informed and wise decisions ultimately. So this is the aim of IoT. Aim of IoT is from the gathered data we extract information, and this extracted information is wisely used in taking decisions. So this is, we can say, the most generalized way of looking at the IoT. So depending upon the now, since it is just anything which is collected, it can be used in almost all the fields. So depending upon the field of application, processing of these data will provide innumerous applications, making smart homes, smart cities, smart agriculture, and you put smart to anything, it becomes one of the part of IoT. Smart cards, smartphones, and anything you can have. So all these are application of IoT. So this is the generic architecture of IoT. Sir, I'm in the lecture. We have this is the generic. You have layer one. Layer one is at the lower. Then you have layer one, which is perceptual. Then on layer two you have network. Layer three is the support, and layer four is the application. So it's a 4-layer architecture of IoT. So when I say layer one, actually as a communication person, we are concerned with this layer, which is this layer, the layer one of perception, because this is the layer which collects the data. After getting data from here, so we collect data. So what we use to collect data, we use a sensor network or simply wireless sensor network to collect the data. Then this data using a gateway is put onto the network. The network is part of your basically the internet, where this data goes. And after that, we use a support platform for then with connectivity we put it on that is your network or infrastructure communication protocols, which is your second part, the network. Then from there we take this data to servers basically, or servers are the support platform with intelligent computing. And it is here where we can use intelligence and bring out the information from the collected data, which is done at this level. This network gives us the connectivity to these servers, and these servers, they are the computing high computing machines which analyze, process, and extract information, and then it goes to the application where people will be using this for services interface. Like example is suppose environmental monitoring. So if my example is say environmental monitoring, then my data collected will be here, which will be done by sensors. And these sensors will be different pollution sensors, your carbon dioxide sensor, nitrogen sensor, nitric oxide sensor, so many different sensors. They will take out different information. All these will be collected using a sensor network. So you may have one sensor network, or you may have a number of sensor networks deployed at different places in the environment. Then from there, all this information through a gateway and the connected internet goes to the network. So once the information comes to the network, from there it goes to a server which is devoted for collecting all this information and taking out its whatever the information you want to extract. Something like, say, if you have a carbon dioxide more than a level, you can inform what this has happened, or carbon monoxide beyond a level, or particulates beyond a level. Then we can inform, say, the places why this is happening. And so all this intelligence will be taken out from there, and then this decisive decisions or the information decisions will be then goes to the highest, that is the application, where it goes to, say, if you find that some factory is suddenly polluting the environment, then a decision is taken, and from here they will inform that factory, okay, this is a problem with you, please check yourself so that you don't uh, do the pollution, and that way this whole thing works. So this is the generic IoT architecture. So for us, the most important is the wireless sensor network, which forms the layer one of IoT. So IoT, this is the thing. Like IoT and wireless sensor network, they both many times are used one with other. But what concept says is wireless sensor network are the layer one of your IoT architecture. So the importance of wireless sensor network is collecting data and giving it to the network. So that is where your WSN works, or wireless sensor network works. So, so wireless sensor networks are the networks in which sensors are distributed in ad hoc manner, so and works jointly to sense some phenomena and information which is gathered is transferred to the base station. So these terms we'll see just after this. We'll see the slide and then we'll see. So wireless sensor network is one of the emerging field of wireless communication, where advancement is taking on the basis of low cost, low power, multifunctional sensor nodes. So wireless sensor networks, they are networks formed by low cost, low power, multifunctional sensor nodes. So you have sensor nodes which are having these properties, and they form a network out of it, and that's called the BSN. So wireless sensor network are complex systems that have ability to automatically and dynamically self-organize its connectivity. So that means if we place these nodes with power, and then these nodes have they can automatically form a network. So they are given the capability to do that. So that is wireless sensor network. And they are dynamically self-organizing. That means for the transfer of information, there are certain decisions which dynamically these networks can take, so that the information from a basic sensor reaches to the base station. So this is the basic we can say. And the sensors, every node, the node that we have will have a small radio communication system. It will have a small computational part, that means it will have a processor, and it has number of sensors which can be put on this node. So the same node can be used. Say if I put a humidity sensor, it can sense the humidity. If I put a temperature sensor, it can sense the temperature. If I put a pressure sensor, it can sense the pressure. If I put a carbon monoxide sensor, it senses the carbon monoxide. And also a single node may have multiple sensors. That a same node may sense carbon dioxide, carbon monoxide, sulfur dioxide, or some other variable. Whereas a node may have only one sensor. That a sensor node may only sense temperature or a pressure. So that depends on the application where we are going to use it. So it forms but every node will have its own computational power, its own communication power, and little bit of what we call it as processing power. So this is again sensor networking, how the networking is done. That large number of sensor nodes are densely deployed in an area. Sensor node can collaborate with one another, measuring the condition of their surrounding environment, like temperature, sound, vibration, pollution, anything. The sensed measurements are then transformed into digital signal and processed to reveal some properties of phenomena around the sensor. Since the sensor node in WSN have short radio transmission range, intermediate nodes act to relay nodes to transmit data towards the SIG node or the base station. So basically, when we say the transfer of information always takes place from the sensor node to the base station or the base station node. So this is our one of the ways of deploying sensor. We'll see different types of deployment also. So here this is random deployment basically. So every node has its own communication limit. So depending upon the communication limits, so this is a base station. These are the nearest nodes, or which you can say here. Here, this is the base station, and you have a nearest nodes which are here. So and the dotted line you can see here. This is the communication range for these routes. So these nodes can communicate with the base station. They can communicate with this node, but they cannot communicate with, say, node 1 cannot communicate with node 9. So these are depending upon their proximity. We have this. So if there is an information that has to come from say node 9, it may take one of the nodes here for hope. So you have one hope. It may take another two hope. This is, and the information reaches here. So or it may take say from here to here and directly here. So this your wireless sensor network, if your node is beyond its communication range, so if this is the communication range, then the information reaches base station in a hoping manner. So there are a number of different routes that the information can take. So like if let's say 10, it may say from node 10, if there is some information, it may from 10 it may go to 6, then 6 may send it to 7, 7 may send it to 2, from 2 it may go to here. So all the nodes. So, and this is basically this is a homogeneous sensor network where all nodes have similar capabilities. That means they have both the capabilities collecting data and routing data. So if both the capabilities are there, then in this kind of scenario, this network can work. Then depending upon deployment, when it comes to wireless sensor network, we can have two types of deployment. One is your random deployment, and second one is deterministic deployment. That means if we don't have any pre-planned, like suppose I want to embed a sensor network in a war zone and in my enemy's country, if I want to put some sensor network there, then you don't have any access to the place where you are putting the sensor network. The reason is it's enemy territory. So there what I can do is I can take some, say, a few thousand nodes and just deploy it by using a missile, or maybe by using simply an aeroplane and drop all these nodes randomly into the area. So once these nodes are randomly deployed, then the sink will be outside this area. So these nodes have to configure themselves into a network, and we get the information by this network to the sink. So this is random deployment. But all the time the needs may not be so stringent. So the other and more what we can say for civilian use, most of the wireless sensor network, we may have the access to the area. So what we can do is we can deploy these nodes intelligently by putting these nodes at the places we want to put it, so that we have a network easily formed. So this is basically deterministic deployment. So when the actually wireless sensor network, when they were developed, their main aim is for random deployment. That means if you just throw the nodes, they should form their network and transfer the information back to the sink. That is what is needed. But we can also have deterministic deployment. Like say, you want to do preventive maintenance of a bridge. So in a bridge, we can have different vibration sensors placed at different positions onto the bridge, and somewhere outside the bridge, we can have our information base station, which gathers this information of the vibration, because we know that before failure, most of time the vibrations increase. So we can keep sensing it, and then before those vibrations from that particular bridge or that particular place becomes more than a threshold, we go for maintenance. So before it collapses, we can do preventive maintenance, and then again keep on monitoring it. So this kind of deployment, this is a deterministic deployment. Or say you want to get the pollution data from a city. So in city we can put our sensor nodes at the places where you have more pollution, so that the readings we can get very closely to the and then we keep on monitoring all those nodes. So that is another example of a deterministic deployment. So in random deployment, the path of sensor node to another node or base station is not defined. The path of transmission of data is chosen depending upon the availability of sensor nodes. So this is random deployment. And in deterministic deployment, the transmission data is done using predefined path organized between the nodes. So in deterministic deployment, we already know where the node is, and so we can always define a predefined path for getting the data out of the system. So this is random deployment and deterministic deployment of the nodes. Then next question, one question normally people ask, why when we can use individual sensor, why to use network of it? So this answers that query. That is, first of all, an individual sensor has a very limited sensing zone. So if we make a network of sensors, we can increase the sensing zone or the wider area of operation. So this is one reason why we should have network other than individual sensor. Then next important thing is redundancy. That means we can use more than the required number of sensor nodes. And since if we have a denser sensor nodes, that means we use more number of nodes than the required one, then we can incorporate fault tolerance inside the sensor network. Because if some node fails, but since there are other nodes which are around the sensor in the area, they can take care of that failure node. So this kind of things. So redundancy gives us all those flexibility to use fault tolerance and so many other things. Then it also improves the accuracy, because when you have a single sensor, you get single reading. But when you have number of sensors, you get number of readings. And if you take mean or median or mode of the readings, you get the more accurate or improved accurate readings. So this is basically your improved accuracy. And next is extended functionality. Sensor node can not only perform the sensing functionality, but also provide the forwarding services, because that is what is needed for the homogeneous sensor network. So this is why we should have censored networks rather than using individual sensor. Then what are the application of WSN? So you have innumerous applications of WSN, wireless sensor networks. So some of the most common ones are environment monitoring, traffic monitoring, flood and disaster monitoring, sensor-based navigation systems, healthcare monitoring and surveillance, event and fault detections, smart homes and cities, and Internet of Things. So these are different applications of WSN. So you have environment monitoring, traffic monitoring. So these are some of them. Actually, you can have infinite number of applications of WSN, because you have sensing, computation, and communication all put together. So once you have these three components put together, we can do anything with this combination. So as far as applications are concerned, we can have very large number of applications for WSN. So these are your network architecture. So basically, when it comes to architecture, we have two architectures which are most commonly used. One is your flat architecture. Flat architecture, it is also called layered architecture, because you have, since the communication range of sensors are limited, so what we can do is that the information reaches to the base station by using multiple. So you have a layer, so first layer, second layer, third layer, and accordingly the information saved from the third layer will reach the base station with minimum one. So if I see the what we can see from here, so you will have first hope. This is your first hope, then second hope, and third hope. So the information from here reaches here by three hopes. So this is your flat. But all these nodes, so all the nodes which are here have the similar capability, and so this is homogeneous. So, and all the nodes should have both uh, your both data. This is sensing capacity as well as communication capability, and that too routing capability. That means they should be able to route data to the next node. And the node here gives to the next node. This node gives to the base station. But the problem with the flat architecture is, if we see any data gathered by any node has to pass through the first layer nodes. So since wireless sensor networks, they are made with using battery operated systems, so the batteries of these nodes, the first layer, will deplete most quickly. So what will happen is, if any of these first layer nodes, if they fail, then the whole network fails, because information reaches the base station through these nodes only. So, and also here we cannot use the power of your aggregation and other things by which we can improve the life of this sensor network. So what will happen is, the layer one, the nearest layer to the base station, they will fail. They will get depleted of energy very fast. And many nodes which are away from here, they may be working, they may have the power, they may have the capacity to send the information, but they cannot communicate with the base station. Reason being, the first layer has already depleted its energy. So this is the problem that you normally see with the flat layer architecture, or a layered architecture, or a flat architecture. Then the solution to this is a clustered architecture. So in clustered architecture, we have base station, and then we have clusters formed. And the bigger nodes, you can see here are some small nodes and some is a bigger node. The bigger node that you are seeing here is a cluster head. The cluster head, CH. So this is CH. Similarly, this is CH. So these cluster heads. So cluster heads, it is they are the boss of the cluster. So they gather information from the sensors and send this information to the base station. So here we can introduce heterogeneity into the sensors, where we can make these cluster heads to be little powered, high powered, and bit bigger nodes which have more energy power, which can last for months and days and years. And the nodes, we can have simple nodes. So what this, since this information to the base station is sent to the cluster head, we can have a special kind of nodes. So heterogeneity can be introduced into the system. And this way, these nodes are the simple nodes which have just, they send the data to the cluster head. Cluster head collects the data and send it to the base station. Similarly, in all the clusters. So these simple nodes in the cluster, their batteries will last more, because they don't have to do much of forwarding of the information. Because as far as you're in WSN, they say that the energy taken for communication is always very large, because it has to be done wirelessly. So whenever you want to do a wireless communication, lot of energy is needed. So in clustering, in a cluster architecture, we can have a saving there. So we don't have to do so much of your forwarding. All you have to do, all the simple nodes have to do is just send their data to the nearest cluster head. So, and also there will be heterogeneity involved in the system. We can also have cluster architecture with homogeneous sensor networks, but that's an old concept, where the cluster head is all the time chosen, and this cluster head will be the one of the node which is having the highest energy and collects the data, send it to the base station, and so every node has a chance to become cluster head. That is with homogeneous, but it is better to use a special cluster head. That means you can use some few high capability nodes and other a large number of low capability nodes. So this way we can have your clustered architecture, and we can also have more efficient use of resources. So these are the challenges in WSN, or also since WSN becomes a part of IoT, so we can also say these are the similar challenges exist with IoT. So the first challenge that we have is energy efficiency and node failure. Now, energy efficiency is one of the most important challenge on which a lot of people are working. Then since these sensor nodes are very delicate, most of the time these sensor nodes fail. So another important challenge is node failure. Then network resilience. Network resilience is because of your node failures as well as change in the topology and the failure of your nodes. The network keeps on changing. So the network that WSN should form, it should be resilient network. That means even if few nodes die, you should have capability to form the network so that the information keep on flowing from the last sensor node to the base station. Then the other challenge is communication failure, because the communication failure can occur because of failure of node or because of distance. That means sometimes we deploy some nodes, but again the distance between them becomes so large that the node is not able to communicate with the node where it wants to send the data. Then you may have another challenge is loss due to the harsh environment. Then you have node localization. Node localization is basically when we do random deployment. Then since the nodes are deployed randomly, we don't know the location of each node. But the location of each node is needed to form the network. You cannot form a network without knowing the location of each node. So node localization or node location becomes a challenge. So there's a lot of people working on this also, where you can are different. But nowadays, because of GPS, so if we put a GPS tag on every node, the node we can localize that node, or the node will get a unique longitudinal and latitudinal address. So anywhere on the earth, it can be localized. But the problem is, if you incorporate all the nodes with GPS, the system becomes very expensive. So still, there's a lot of work going on node localization. Then the fault tolerance, because you have the nodes are in the open environment, so there always exists the danger of developing faults, and there are certain things which are already available in our atmosphere, which is something like, we say, noise. Since noise is already there, so these noises can also give rise to faults. So what we want is, we want the wireless sensor network to have some capabilities of fault tolerance. That even if few nodes fails, or some sensors become faulty, or because of some noise it's not able to communicate properly, still it should have the capability for fault tolerance. That is, small faults it should be able to tolerate. Then coverage and connectivity. Now these two things are different. Coverage we are talking about here, and connectivity. Coverage is to do with the sensing coverage. That means, say you have a sensor node, and this sensor node you are sensing, say temperature. So it has a sensor node, you are sensing temperature. So it will be sensing temperature of some area which is here. So this is its sensing coverage. So if I want to sense temperature somewhere here, then I have to deploy another sensor node, because this same cannot sense from there. So this has some sensing area around it, which is a sensing coverage. The connectivity is basically the communication part. That means if you have two nodes, they may not be in the same sensing zone, but they might be in the communication zone. So this is the communication which to do with connectivity. Whether this sensor is able to connect to this and say if this is a base station. So if it is a sensing some temperature here, it can send its information to this sensor, and this sensor node can send it to the base station. And this is how it can work. So sensing sensing coverage is the area around the node up to which it can sense the sensing parameter. So if it is temperature, it may be humidity, it may be anything. So that is a sensing coverage. And connectivity is its communication coverage around it, where it can communicate with the another node. So this is the communication coverage. So connectivity is because of communication coverage, and or connectivity, and sensing coverage is this the area around it where it can sense the parameter. Then another challenge is resource consumption, because these are small sensor nodes are designed. They are very small nodes, so they have limited energy. They have limited processing, and also they have limited communication. So since they have limited communication, limited energy, limited processing, so this is a highly resource constrained system. So since it is a highly resource constrained system, whatever resources we are using, we should use it as efficient as possible. All kind of optimization can be used for this. So the resource consumption, we have to optimize the resource consumptions. So because all the resources that it has are very limited. So since you have to work with those limited resources, then we have to develop all kind of resource constrained systems. And so we have to be very careful with the resource. We have to be very careful with the resource consumptions. Then we have fragmentation. Fragmentation is basically broken into small parts. So since it is made up of large number of nodes, so any link can fail or any node can fail. So you may have a node failure, you may have link failure, or so there is fragmentation. So we have to take care of that also. So which means that we should put inside the system some sort of tolerance. So if there is fragmentation, it can be we can sort it out with some form of tolerance. So tolerance normally comes with redundancy. So you have to put more number of nodes, go for larger number of. You have to put some ideal nodes, which we only use when some of the other node fail. So that way we can have some sort of thing. Then the other thing is, since this is exposed system, it's a wireless system, so we have security issues. And security issues, and most of the time these security issues due to anomalies. Now we'll see first what exactly is anomaly, and then we can come to this. So these are the security issues in IoT. That is according to State of Art survey. So top 10 most important security issues which are there in IoT are insufficient testing and updating, brute forcing and issue of the default passwords, malware and ransomwares, bonnet AB cryptocurrencies, data security and privacy issues, small IoT attacks, AI automation, home invasion and remote vehicle access, untrustworthy communication. So these are the security issues that are there with IoT. So let's first come down to anomaly, and we'll see what exactly is anomaly. An anomaly is observation that seems to be inconsistent with the remainder of that data set. So that is how we can say. So say you have this is one N1, this is our N1 which is one set, N2 is another set, and we have some which are outside these sets. So we can say that say if this is one cluster and one is cluster, you have one which is away from this cluster. We can easily say that O1 is an anomaly. O1 and O2 they are anomalous. And if we see this O3, this is a cluster of anomalies. That means you can have even a cluster as anomaly. Anomalous basically means which is inconsistent with the thing. Like so, the example I can give you is say observation which is inconsistent with the remainder. Suppose in a room, or say in a room, this is my, say I have one room, and in this room I have deployed 1, 2, 3, 4, 8, 9, 11, 12, 13, 14. I have employed 14 numbers of temperature sensors. So I have employed 40 number of temperature sensors, and I'm looking at the reading of all these sensors somewhere here. So my temperature reading I'm getting. So I have say I have n equals to 14. There are 14 number of sensors. So I have say n1, n2, n14, and I'm getting the readings. So since it's a room, it's one room. Say this is showing 25, this is showing 25.1, some is showing 26. There is one which is showing 40, some is showing 36. So now, and say most of are showing around 25. So in this room, if you see in room, the temperature will not change so much, because in a room temperature, say one side of the room you may have sun, so temperature may be say 26. The other end you have shade, temperature may be 25, and in between you may have some temperature gradient like 25, 25.1, 25.2, 25.3, 25.4, and that way say you have 26 here. This much variation only. But if you look at the reading, you suddenly find some are showing okay 25, 26. So these are normal reading. But there is one reading which is showing 40. There is another reading which is showing 36. So this 40 or 36 reading, just by looking at it, we can say that they are anomalous. Because here we can go for the majority voting. That means if majority of the sensors are giving reading around 25, then we can say 25 is the temperature in the room, and the readings which are outside this 25. So what we can do is we can put a threshold, say 25 plus minus 0.5, we can say are correct. Anything beyond this, we can call it anomalous. So this is basic. So anomaly is when your observation seems to be inconsistent with the remainder of that data set. So this is anomaly. So we have used this anomalies to do a number of things. So then in WSN, what are the different types of anomalies that can exist? So in WSN, we can basically have three kind of anomalies. First one is your data anomaly. Second one is node anomaly, and third one is network anomaly. The data anomaly is basically associated with one functioning of sensors. So because in the sensor node itself we have the sensor. So this sensor may not be giving the correct reading. So if you have more than one sensors put around in a place, and we are getting all the reading from there, again we can looking at the readings that we are getting from there, we can easily classify one of the sensor which is not giving the correct reading as an anomalous sensor. Then other is we can look at the change of the reading from the sensor. Like suppose there is one sensor for last 1 hour is giving the same reading. So we can say this sensor is stuck. It is stuck at something and it's not actually sensing the variable. So that's another way of finding out whether this sensor is stuck or not. So this we can then exclude from our actual readings that we are getting. Then so the data anomaly we can have at the sensor level. So this is at the sensor level. Then the node anomaly is associated with one functioning of node. So in a node you may have more than one sensor. So it may have one of the sensors may not be working, some other sensors may be working. So that is your data anomaly. So that directly comes into the sensed data. Then the node anomaly is suppose sensor may be working but the node has failed. Node has lost its battery, node has lost its communication link, and so node has failed. So that is your node anomaly. So when you have say malfunctioning of the node. Then network anomaly is associated with the network itself. So if more than few nodes are malfunctioning, then the network itself will have anomalous data. So that is network anomaly. So we can look at these 3 types of anomaly in a deployed sensor network. So first, these triangles you are seeing here, they are the relay nodes, and these pink cylinders you are seeing here, they are the sensor nodes. The one which is white is a faulty node. So that is just to show you the anomaly. So with the sensor, this one is a sensor node. So in sensor node, if your sensor itself not working, then we have data anomaly. If your one relay node is not working, so it won't be able to send the data sent by other nodes to the base station. So we have node anomaly. And if more than few nodes, they have node anomalies and they are networked together, then that is your network anomaly. So we can have, in general, we can have data anomaly, we can have node anomaly, or we can have network anomaly. So in data anomalies can be further classified into three classes. Temporal anomaly. Temporal anomaly is basically where the problem is in the time. That means high variation in subsequent readings, lack of change in sensor reading, gradual reading, or out of band reading. So these are temporal anomalies. That means with time. So with time, like some sensors they may give very erratic readings. Just now it gives 10, after some time it gives 20, then 30, then 10. So the variation is in the subsequent reading is very large. So that is one kind of anomaly we can have, temporal anomaly. Then the lack of change in sensor reading. That means the sensor is stuck to one reading and is not changing at all. Then also it has anomaly. Because sensors with time, the sensing parameter will change. So because we always sense a parameter which changes. So if it doesn't change means there is some anomaly. Then lack of change in the sensor reading, that gives rise to anomaly. Then gradual readings. That means it is giving very slowly changing readings. Then out of band reading. Out of band reading is anomalous basically when all the sensors around it are giving different reading, but it is giving some reading which is beyond the other sensors out of band reading. Then this is temporal anomaly. Then we can have spatial anomaly. The detection of this type of anomaly requires the comparison of sensors with other sensors in the network and surrounding sensors. So this is spatial. That means around the space itself you have some anomalies. So but your temporal anomaly is for the same sensor node in the subsequent reading or in the time scale. But spatial anomaly is basically when you have many close sensors and they are giving their readings quite differently. So that there is you have spatial anomaly. And when you have both temporal and spatial combined, we have spatio-temporal anomalies. The spatio-temporal anomalies comprises both spatial and temporal variations. In the case one or more than one node can be involved. So that is your spatio-temporal anomalies. Then we have node anomalies. The sensor nodes are the network of multifunctional devices which are easily damaged. These unshielded sensors, which are not tamper resistant, are exposed. So what we can say is the primary cause for node anomaly is battery issues, secondary battery issues, node failures, and node resets. So these are for the node anomalies. Then network anomalies, the anomalies that can occur due to the failure of the gateway, and sometimes the node failures, malicious attacks are due to the unavailability of transmission radio. So network anomalies normally is because of connectivity loss, intermediate connectivity, routing loops, broadcast trunks. So these are the cause for network anomalies. So as there are anomalies, there are also detection techniques. So we can say anomalies. We have detection techniques classified based on the architecture algorithms that are used. So basically, there are three approaches for anomaly detection. First one is centralized approach. Second one is distributed approach, and third one is hybrid approach. Centralized approach is basically when we have one center element which takes care of all other nodes and finds out whether there is some anomalous reading in the node. That is centralized approach. In distributed approach, many nodes in the network will have the capability to detect anomaly, and then anomaly is detected, and then it is passed on to the base station. And hybrid approach is basically using centralized and distributed approach intelligently. So that is hybrid approach. Then, depending upon your detection techniques, we may also have classification for anomalies. That is your signal processing approach, you have distributed approach, you have hybrid approach. So these are different approaches for detection techniques of anomalies. So this is here we can explain the centralized approach and distributed approach. So this, as I told you, in centralized approach, anomaly detection is done, say, at a base station. So data is this. If you see here, these are two networks which are same. This is cluster network. So you have, say, S1. These are the sensors, and this is cluster head. So we have different cluster heads. So these cluster heads, they are connected to the base station, and each cluster head is having some nodes under them. Like this is one cluster, which is having 1, 2, 3, 4, 5, 6, 7, 8 nodes under this. Then similarly, this is another one, another cluster, and this is having its own cluster. So both the networks are same. So if we so anomaly detection is done at the base station. When all this information comes here in the base, we analyze this information and find out the anomalous reading, and we only pass the correct reading and take decision depending upon the correct reading and avoid the anomalous reading. So this is centralized approach. So all the things. Now your distributed approach. In distributed approach, what we do is the cluster head that we have, we give them the capabilities to detect the anomaly. So if the cluster head can detect the anomaly in their own clusters, so what this cluster head will do is they will send only the unanomalous data to the base station. So base station get unanomalous data. So you this again from here also you get anomalous data. So the node itself has the capability. So cluster head node has the capability to detect anomalous data locally. So advantage here is each cluster head can detect the anomaly. So this is a distributed approach for the anomaly detection. So definitely your distributed approach will always be much more efficient then the centralized approach. Because in centralized approach, all the anomalous data will also reach there, and then we select only the good data out of the anomalous data. But in distributed approach, the unanomalous data will not reach the base station. So base station will already get the filtered unanomalous data. So the anomalous data can be avoided at the cluster head itself. So this is your this is basically the difference between the centralized and distributed approach. Then we have hybrid approach. In hybrid approach, what we do is the cluster heads, we use both techniques of your first and second technique together. That means the base station still has the capability, because chances are there, even if we have unanomalous data reaching to the base station, but if cluster heads are not fully removing the anomalies, still some anomalous data can reach to the base station. So here what we can do is, we give the cluster heads the capability to detect the anomalous data and avoid sending anomalous data to the base station. But also we give the your base station the power to find out from the collected data if still there exists some anomalous data. So it is basically this is the hybrid approach, where both cluster head as well as the base station is given the power to determine the anomalous data from the data that they get. So this is the hybrid approach. So these are your anomaly detection based on the systems. So basically we have three different three different approaches. There is signal processing approach, statistical approach, and machine learning approach. Machine learning approach is one of the latest approach for anomaly detection. So in machine learning approach, we have bio-inspired, non-bio-inspired based on data. So in bio-inspired, we have ANN and AIS based. The non-bio-inspired, we have classification and clustering based. And on data, on the collected data, because in machine learning, the data-based are most used algorithms. So we can have supervised, unsupervised, and semi-supervised machine learning based on the data that we get. So, and similarly, you have statistical approach and you have signal processing approach. So since we are dealing with the machine learning, so we'll be only talking about the machine learning. So machine learning in IoT. So we can use machine learning in IoT for many applications for solving the security issues of IoT. New and traditional machine learning algorithms have successfully handled the challenges of IoT. The use of machine learning to aid security and detection in IoT environment has become extremely important and face the challenges. Machine learning is a subsidiary of well-known technology, that is artificial intelligence. Now, actually, I wanted to just this one slide. I wanted to give this slide. This is because I've seen people have a lot of confusion with deep learning, machine learning, and artificial intelligence. So I just want to clear this for this confusion. That is, when we talk about machine learning, what we are talking, and when we talk about deep learning, what we are talking, and when we talk about artificial intelligence. So actually, if I say from the set theory point of view, then I can say the artificial intelligence is universal set. And subset of this universal set of artificial intelligence is machine learning. So machine learning is one part of artificial intelligence. And inside inside machine learning, we have one more part or subset, which is deep learning. So what I can say is deep learning is a subset of machine learning, which is a subset of artificial intelligence. Now, if we want to come, say in normal language, what it means, artificial intelligence is basically giving the machines we talk here are can be a computer, can be a car, can be a robot, can be anything, any machine. If I try to give this machine some human capabilities, like say to a car, I give it a self-driving capabilities. That means in the car it doesn't need a driver, it will drive itself. Self-driving capability, or it can park itself, which is or nowadays is available in many expensive vehicles, which can park themselves without driver. So this kind of capability is given to the machine. This all these things comes under artificial intelligence. So we can give some small kind of then machine learning. Machine learning is actually when this artificial this done when we try to teach machine a human-like behavior. That comes under machine learning. So machine learning are some algorithms which are developed, well tested, and then if we give these algos to these machines, they have the capabilities to take a little bit of intelligent decision. So that is machine learning. So in machine learning, basically, in machine learning, what's done is we teach these machines from data that is there in already a labeled data. That means you have some data which is already labeled, and we give it to these machines. So what we do is, because if we know that when we say machines here, the machines here basically is kind of a system. Say machine is any system which has some input and we get some output. Say something like if you have a X car, so you have acceleration. So this is the accelerator pedal. So when you pedal the accelerator, the speed increases. So when you input is pressure on the accelerator, output is speed increases. So that way, so anything can have some input and you have some output. So between this input and output, there lies some relation. So if I have a black box and I give it all the combinations of input and their appropriate outputs, then what happens is irrespective of any input comes, it knows what will be the output because it is already stored in it. So if I make a machine in that kind of manner where I introduce all possible inputs and teach the machine appropriate output, that is machine learning. So in machine learning, what we do is we train the machine. So what we do is we keep on giving the sets of input, fine tune the what we call it data features, and then after fine tuning the data features, we look at the output. We take a threshold accuracy as the required accuracy, and then we say the machine is trained if the accuracy comes down to some predefined level, say 99.9%, maybe 99.999%, and then we say the machine is trained. So here what we have done is if you look at here, the features that we make the machine work, we do it through using machine learning algorithms. But here the involvement of human is there. We do it with every time keep on iterating, keep on running by changing the parameters, and at a final parameter we get the best results. We say, okay, we cannot go beyond that. This is the best this machine can do. This is machine learning. Now, deep learning is also machine learning, but here what we do is, instead of manually and with experience fine-tuning the features, we let the machine take the decision and fine-tune itself. That means the feature selection is also done by machine itself. And that's why in deep learning, we need machines having very, very high computational capabilities. So this is deep learning. So this is basically artificial intelligence, machine learning, and deep learning. So deep learning has also attracted considerable attention in recent years. Currently, it is recognized as the relevant approach for the network intrusion detection in network, utilizing pattern recognition, image processing, and text mining. The method of machine learning and deep learning are singly hand, singly, single-handedly capable of handling and the analysis part. So these are now where in IoT we use machine learning. We have already seen at this is at the lowest level. We are generating data, then we are collecting data, that is at the network level. Then we analyze. So this is at the server level, which we have shown there, where we have analysis. So machine learning in IoT will be used for the analysis of data. So data analysis. So this is where we use the machine learning in IoT for analysis. So you have generate, collect, analyze, act, and visualize. Generation. So this is where you have WSN. That is wireless sensor network, or PLCs, SCADA, all these. These are also sensor networks which are sensing PLCs, SCADA. These are the SCADA is for power data. You have PLCs for logic controllers. That is the programmable logic controllers. Then you have sensor networks, which is generating data. Then we collect the data. Data comes, say this. Then we send the data to the servers where it is analyzed, and then we take the decision on analyzed data, that is acting upon it, and also the visualizing, that is how the data pattern, what is the pattern there, or ultimately say if you are analyzed, say if you environmental monitoring, whether right now there is, we can visualize whether the environment is okay or there is some problem, that kind of thing. So this is where machine learning we can use in IoT. The machine learning is used at the analysis part. So this is how we can use machine learning normally. So we have some label data. Label data is basically when we know the relation between input and output, then we call it as a labeled data. That is the data for a given input, what is the output. When it is known to me, that is the labeled data. So we have some labeled data. Then we have some machine learning algorithms. We pass this labeled data through these machine learning algorithms, and we train these machines. So in machine learning, we have two phases. First is the training, and second is the prediction or the use. So once we have labeled data, we train the machine using the labeled data and machine learning algorithms, and then I have output. So the output that I will have will be the model, which I called it as a learned model. So this learned model will be the trained machine or learned model. And then we pass the data again and see at the prediction. And if we are getting exactly the same, that is when I give this label data again to it, it is giving me the same output which was supposed to be there is correctly. So from there I get the prediction. Now if this prediction is 99.9% near to whatever data is, I can say my model is trained. So if I have a trained model, then I can use unlabeled data. That means I can use the real-time data and then see the prediction and then find out whether this is really working or not. So this is the entire gimmicks of machine learning based models. So you always start with a data set. We make a machine learning algorithms, make it learn, get a learned machine, pass some portion of data set, see the accuracy, then we let the unlabeled data set go through the learned model and again look at the accuracy. And then if our accuracies are still good, we say we have a well-learned machine or a learned model. So these are the different types of machine learning algorithms which are used. Linear regression, logistic regression, decision tree, SVM, Navy Bayes, KNN, K-means, random forest, dimensional reduction algorithms, GBAs are gradient boosting algorithms, So these are the things, these are the algorithms which are normally used in machine learning. So now I'm going to give one example of how we can find intrusion using anomalies. So what is intrusion? Intrusion is basically the what I can say is intrusion is when somebody intentionally do something wrong into the network. That is intrusion. Anomaly can happen naturally. It may not be intrusive alone. So we can use, but we can, since the characteristics of anomaly and intrusion, they are more or less same, because man-made anomaly can be considered as intrusion. Anomaly which is made by men can be considered as intrusion. So intrusion directly affects the data in the network and thus changing the data pattern, which is affecting the features. So since intrusion is very closely connected to anomaly, we can have, so the most commonly used methods for intrusion detection is anomaly based IDS. That is intrusion detection systems which are anomaly based. So these are the reported intrusions in IoT, which is denial of services, user to root, remote to local, probe attacks, brute force attack, web attacks. So these are different intrusions which happens in IoTs. So this is just in this. So thus, so this is our problem that we are formulating. We are trying to uh, find intrusion with this. So there exists various security challenges in IoT based on the application utilized and exposure. So our observation is the security challenge follow a pattern. So the solution for this we have given is based on the security channel and challenge, an automatic trained system is required for self-training and diagnosis of the fault security issue present in the network dynamically or on fly. So it's basically the uh, problem formulation is a very generalized problem formulation for making a intrusion based anomaly based intrusion system. So intrusion detection system, that is IDS, where IDS are located in IoTs. So you have depending upon you, we have again three types of IDS: data IDS, node IDS, and network IDS. So depending upon whether we have data intrusion, or we have node IDS, or we have network, we can have IDS at three different places. So IDS at the data, for the data IDS, there is infected IoT devices. So we can find out the infected IoT devices by using data IDS or data intrusion detection system. See, then using anomaly detection at the node, we can use, we can get the your node IDS or node intrusion detection system. So for node intrusion detection system, the anomaly has to be detected on the node, and so we can run this at the security gateway and find out whether there is an anomaly or not. And then for network IDS, it has to be run on internet. So that will be running on the servers, basically IoT services, device driven. So in general IDS operation, so this is your IoT components which are there, sensor node, smart physical objects, and what IDS does is it keeps on monitoring these sensor nodes and things. After monitoring, it catches the pattern matching algorithm. We use the pattern matching algorithms and keep on observing the patterns on it. Then if there is a predefined malicious pattern set is already there, and if it matches, this pattern matches with this, it gives a attack response. That means it tells there is an attack or there is some intrusion, and accordingly the action goes to the system, alerting the system that there is some intrusion in the system. So this is how your IDS work. So intrusion detection. So what I can say is, IDS just keeps on monitoring the. It may be sensor nodes, smart objects, IoT components, any component where it is, it's monitoring that component. So it is data that is actually monitoring the data that is flowing through it, and it's keep on checking the patterns which are there in the data. If these patterns they violate the normal matters and it matches with some predefined malicious set of pattern, then it detects it as an intrusion, and it gives attack response, alerting the system that there is intrusion. So this is how your IDS work. Then security based. Now when we try to find, we design an IDS based on anomaly. Then we can have 4 different situations which can happen. That means the system was intrusive but not non-anomalous, or your system was non-intrusive but anomalous. Your system was non-intrusive but non-anomalous if you have intrusive and anomalous system. So these are the 4 conditions can happen. Now what we are doing here is we are using anomalies to detect the intrusions. But anomalies and intrusion may not exist together. If our system will work very well if there is anomalous behavior whenever there is intrusion. So for the 4th one, we will have the best response. So we can see them one by one and try to understand. First one is intrusive but non-anomalous. That means so there was some intrusion in the system, but the intrusion did not produce an anomalous behavior. So there was intrusion in the system, but the system did not produce it. So what will happen is our system, which is based on anomalous, will not detect this intrusiveness. So since activity is non-anomalous, then IDS may fail to detect this type of activity. So what we can say is this may be reported as false negative, which means that intrusion is absent but actual intrusion is present, but it is giving an absent there. So I can say that in this kind of behavior, our system will give a false negative. That means our system IDS based on anomaly will not detect this intrusion. Intrusion was there, but since this intrusion was non-anomalous, so it is not detected. So that's why this will be reported as false negative. Then it is non-intrusive but anomalous. That means there was no intrusion, but it produces a kind of anomaly in the system. So our IDS will report it as intrusive, whereas there was no intrusion. But so this we can call it as false positive. Similarly, non-intrusive but non-anomalous. That means our system is going to detect anomalies, but it will not detect anomaly. And there was no intrusion also. Since there was no intrusion and it is not detected, so it is true negative. Although it is not detected, but we don't want it to be detected also because there was no intrusion. Then intrusive and anomalous. So if your intrusive behavior also is anomalous, then our results will be true positive. That means those intrusions which produce anomalous behavior will all be detected. So this is your basically using. So these are the general components for IDS in IIT. So we have this. So intrusion detection schemes in IITs, actually we have these are the 4 normally used signature-based scheme, anomaly-based scheme, and specification-based schemes, and hybrid schemes. Signature-based scheme is when we know the signature of unknown intrusion, then we can detect that kind of intrusion by just seeing the signatures of that thing. Then second, now, but signature-based scheme, they have a problem. The problem is any zero day intrusion. That means a very new intrusion, which do not have any pre-signatures, which is not detected so far, cannot be detected by signature-based. Signature-based scheme work efficiently for that kind of intrusions which are already detected. That means we already know about them. Then signature-based scheme can work very well. But anomaly-based schemes for intrusion detection, they can work even for those intrusions. It will work for all the intrusions that produce anomalous behavior. So irrespective of whether it is a new intrusion, old intrusion, or a recent intrusion, it doesn't make a difference. It will work for all. And that's why anomaly-based intrusions are preferred, because it can even detect the very latest kind of intrusion that some hacker might have put into your system. Then specification based, again, they have the same problem. And a better one is hybrid, where we can mix up these schemes together and get a better result for intrusion detection. So this is again the same thing, whatever I told you. Signature-based techniques, anomaly-based techniques, and distribution-based techniques, and hybrid approaches. Use concept of all the things together to get the rates. So then now this is now from here onwards is the one of the studies that were carried out by my PhD scholar, that is Shang Gavil, who is very recently passed out, and it is all his work, whatever we have done on this. So this is we simply what are the contribution in our first study. We have it is basically we developed a multi-level hybrid anomaly detection scheme for industrial wireless sensor network. So that was our aim. And here we have used a rank-based correlation method, a Spearman's rank correlation method, in order to find the correlation between member nodes and cluster heads. So this is rank. Basically, rank is when you give a numeric value to someone, like say when you are having when you make a merit list, you have rank 1, rank 2, rank 3. Same way we have by using Spearman's rank correlation coefficients, we can rank. So what was done here is we give a different rank to the anomalous readings and give a different rank to the non-anomalous reading, and that is how we differentiate between anomalous and non-anomalous. Then new multi-level, that is your SMO SVM, Spatial Minimum Support Vector Machine, and OPELM, optimally pruned extreme learning machine. These two are classifiers basically, which we have used to classify your multi-level model was proposed to maximize the performance of anomaly detection. And then we use K-method for the clustering, for data reduction, and to build our training data set. So this was the methodology. So anyone who is interested, you can later on go through it. You can understand the methodology. Then these were our results that we got at different things. So you can see here, like humidity and this is the temperature. So you will find that these all the temperatures 24, 24, 24, 24, 23, and then 17.7 node 5, which are very near. So it has a different. It's reading. This temperature is humidity is quite different from the others. So this is given a different rank. So this is a rank, and others are given the same rank. So it looks anomalous. That's why it is given a different rank. So you have rank 1, and similarly you can see others also, and that way it was working. Then this is your complete flow chart for data reduction using K-method. Then framework for anomaly detection, how we have done. So you have at cluster head as well as at the, because this is a hybrid model, so we have anomaly detection at the cluster head as well as at the base station. So some we do it as cluster head and other we do it in the base station. So this is data detection proposed methods. So this is the results in terms of overall detection rate. So by our proposed model, you can say our detection rates are 98.9, 92.5. This and these were your different all other methods. So these are the comparison. Then this is result comparison of similar models. Then overall result comparisons with the similar models. Then these were the publications which has come from this work, that is data fusion, which is September 2021. Two of them have came in September 2021. And there's recently one more has come in expert system, which is impact factor around 7. So there were 6 publications which came out of all this work that we did. Then these are the references that are used. And thank you. Any questions?
Sir,
Yes.
I have a question that is there, may there be any situation where we suppose we implemented hybrid scheme for intrusion detection and we need to compromise with the efficiency as compared to that signature based anomaly intrusion detection system?
Yes. Actually, if you go about the efficiency of signature-based intrusion system will be always better than anomaly-based system.
Okay, because yes, sir, yeah.
The reason is
They
very
are
clear.
already detected. Means
Yeah, it's
signature
already
is
detected, and so that is going to be better.
yeah.
But for zero-day attacks,
Yeah.
Where you don't have any signatures with you,
Right.
they cannot be detected by.
Okay. Yes, sir. Yeah. Yeah. Thank you so much, sir, for such a wonderful session. It is very much knowledge enhancing, sir, and we are very grateful to you for this session. And I just want to say to all the participants, please turn up with your video cam so that we can take the snap for this session.
So any further questions? Mr. Ravikant, you unmute your mic, please. Mr. Ravikant, you're saying something, but we are not able to hear it.
Ravi, sir, are you there?
Sir, actually, sir, we want a group selfie, sir. Sir,
Okay,
please
okay.
stop sharing the documents, sir, actually.
Okay. I thought you were
Ji, sir.
asking something.
Ji, ji. Just want to take a group selfie for the session, sir.
Sure.
Raghuvanshi sir, thank you very much, sir. Dr. Siddharth Chaubey here.
Nice knowing you, Mr. Siddharth.
Sir, it's a wonderful session, sir, for knowledge and all. Sir, very good session.
Thank you.
Okay. Thank you, sir.
Most welcome.
Thank you so much, sir. Thank you so much, sir.
Most welcome. And if you have any questions, you can